if we look at an acceleration versus ramp slope graph, we can hypothesize that there's some ideal correct acceleration versus ramp slope data. That we have some line, some straight line here for small m that gives us a very good result for the correct acceleration, okay? That gives us the actual correct acceleration on an ideal slope with no friction and no other errors. Now we might ask what sort of errors can arise. One possible error, the table that we're on slopes. Remember that we are often determining the slope of the graph by measuring the height of one end of the ramp and the height of the other end. If the table itself slopes, we're not going to get an accurate slope. The slope of the table is going to be added to the slope that we obtain when we measure from the table. Well, this is an error, but it's not going to affect the final result of this experiment, because all that's going to do is it's going to shift our m values. It's either going to increase our m values or decrease them, depending on which way the table slopes, in the same way as the ramp or opposite to the ramp. And that's going to have the effect of shifting these blue points over to the red points. The shift, though, will be equal in magnitude to the slope of the table, so that all points are going to shift to the right by the same amount, and that's not going to have any effect on the slope of this graph. And since it's the slope of the graph that we're after, we don't worry about the fact that the table might be sloping slightly. Another effect is the effect of friction. Now, the effect of friction is, if the effect of friction is constant, this word's cut off here, but if the effect of friction is constant, then what that's going to do is it's going to decrease our estimate of the acceleration. The accelerations that we obtain will actually be lower than the accelerations that we would ideally get if there was no friction. However, again, although it doesn't really look at here, this line is pretty, it's not all that linear. And these things don't all go down by the same amount, but they should. If these points all go down by the same amount, the effect of friction is again going to be, it's going to be a systematic error, but it's not going to cause any change in the slope of the graph, because all the points go down by the same amount. Where the line we get here will just be a lower version of this line. It'll have the same slope. So again, we have no effect. So to the extent that the effect of friction is constant, and it should be very nearly constant on small slopes, this is not going to be a source of error in our final results. However, a consistent time shortening error is highly nonlinear. It gives you this sort of behavior. The reason being that for greater accelerations we get shorter times, so that our error in timing, okay, we're going to have the same shortening at the beginning and at the end of the interval, we assume. And if we have the same shortening, it's going to have a greater effect in shorter times. The shorter times correspond to the greater accelerations, since the cart is going the same distance every time. So we get this highly nonlinear. We don't even have a straight line graph to fit a straight line to, and the slope is going to be all off. So again, this consistent time shortening error is the most serious source of error among those that we've mentioned.